My name is Reed, and I'm the CTO and founder of Jatomate. It's an international consulting company around data. And I'm going to share in this community my experience from different topics over time. And you're welcome to ask questions, challenge, make a discussion, whatever works for you. And the idea is that we all enjoy together. There's no commercial background for this community. It's just for fun, knowledge transfer, and pure networking. So feel free to open your mics, your videos, and make a discussion out of everything. We have about 90 minutes we can use as much as we like. And if needed, we can do another session. This is about building a community and helping each other. So let's get started. According to the agenda, there's 2 more minutes and for people to join, and so we can use those 2 minutes for networking. Is anyone here willing to step up and introduce himself?
Hi, I'm Jay. I work in E-Trade as a C++ programmer, but most of my passion is automation and data. Yeah, I have done one implementation of Airflow and a couple of implementation of Snowflake, database. That's it. Nice meeting you, everyone.
Nice meeting you. You're more than welcome to participate in this and ask follow-up questions after the session. Okay, so without further ado, I see people are still joining, but let's get this show on. I'll start with some basic admin stuff to utilize their time. Just a little bit about us. Bigger Data Demystified is a community. It's worldwide. These are only the international groups. You can see that many groups are around the globe. The idea is to have a reach as broad as possible and to talk to people as much as possible and basically to help each other. There's no commercial motivation behind this meetup, even though I'm a consultant. This is not where I get my new job. This is purely for fun, to speak about my passion and to get to know people around the world. So these 29 groups across 23 countries, as you see, are scattered around the world. There's additional Israeli groups, about 4,000 members in Israel. And we have a website that every past meetup is uploaded here. So you can see the top 3 lectures in terms of interest here, and everything is divided according to categories. For instance, if you're interested in architecture, highly popular theme of this community. There's lots of blogs and meetups in English and in Hebrew, Israeli. So we only speak English, a little bit of Persian and a little bit of Korean. So my lectures are only in English and Hebrew. And that's it. We can discuss today's session. We're right on time. I'm going to mute those who just joined. Feel free to unmute yourself when you want to talk or ask a question. You can use the chat as well to ask questions, but someone needs to bring that to my attention. So please feel free to talk. It's an open session, as I said. Let's get started. So today's session came from a real life use case or scenario I did with a customer when we had to discuss the main differences of deploying Lambda or using a multi-threaded Python script to get lots of data from API vendors. The use case is not trivial because there are lots of APIs and lots of dimensions in the data. Means there's about 1 billion requests per day. So issuing 1 billion requests per day for APIs is usually not easy thing to do because the source API usually totals your amount of requests per second. So, small disclaimer, I may not be the best, but I really love what I do. So you're welcome to challenge me and talk to me. Send me email with comments. You can contact me via LinkedIn, and I will be happy to assist anywhere I can. You can introduce yourself in email if you like for others to review. And regarding the channel, someone asked, I will talk about this, the channel, the video included. I'll talk about this in the end of the session. Okay, lots of exciting, very exciting. Okay, so a little bit about the community. As I mentioned, a very large community globally speaking, but we focused our sessions on 3 areas: on AWS area, which is highly complex by itself; on general matter, this is big data demystified; and BI and analytics use cases. So in the past, everything was very simple. Standard 3-tier application, operational database, and a data warehouse, and the background, and API and the web, and everybody were quite happy. Then came big data, meaning the amount of data that companies started to collect grew exponentially, and the infrastructure started every week. And that became a challenge, and the entire paradigm, architecture, methodology has begun to evolve. Then came the cloud. The cloud came with its own methodologies and challenges, such as cost. In the end of the day, we need to think as architecture of the cost of the architecture and what will it cost us to go moving forward once we scale up. So I would suggest a framework on how I look at things down the road in this lecture, and I hope you'll find it useful for your day-to-day operations. And the biggest challenge there is around data, that the amount of tools and solutions and open source technologies keep growing. This is a rather old slide, and you can see that I haven't been able to fit everything into the screen. So my solution is usually to approach most problems using a combination of cloud methodologies and big data methodologies. In the end of the day, this is what I think is the definition of data engineering. It's all about faster, cheaper, and simpler solutions for your use case. Any questions about this intro before we dive into details? Okay. So today's use case is rather complex, and the audience is rather diversified. So we're going to go over some jargon. There's 2 layers of the jargon. One quick list of the jargon, and then I'm going to go over them one by one. They are important in today's session. Please feel free to ask me questions, so it will be easier to understand. This is a rather technical presentation. Oh, there's a question here. About big data processes, what do I mean? Processing data is a challenge. Ingesting the data from your relevant sources, transforming and cleansing your data, and then modeling it into one sensible model that you will be able to analyze it quickly and efficiently as a data analyst, connect it to your data science team to create your machine learning algorithm, and then present it to the rest of the company. This, in the past 10 years, has become rather complex. The amount of advanced architecture has risen dramatically, and there's constant changes and constant developments around it, which saves time, effort, and frustration around data, because lots of architecture nowadays suffer from one major thing. 80% of all data projects around the world fail due to several reasons, but the majority of them, that the number one reason is that people don't trust the data. And for me, after seeing lots of companies investing a lot of money and effort to build a scalable big data platform that will collect everything and spend lots of headache making it happen and then to fail, it's really a challenge. I hope I answered your question, Mr. Volume 999. Okay, so let's start with the jargon. So we're going to talk about many things today that are related for the use case, but let's go over them one by one. Orchestration, simply scheduling processes. I'm going to dive into them soon. Cluster is simply a group of signals, and Airflow is an open source Python app designed to perform data orchestration over here. Multi-threading, it's a code practice designed to utilize your CPU servers by allowing parallelism. Round robin is an algorithm that mimics true concurrency by splitting the CPU time over more threads. Distributed workload is a workload that runs several tasks on several servers in a cluster. So yes. Modules. Essentially a scenario where you have an application bottleneck. The application is asking more threads than the OS can provide, and the threads are racing each other for the CPU time, and thus we're waiting too much. CPU time, and essentially the performance degrades. A question from the audience: is there an architecture to span threads across NUMA architecture, or are all processes single threaded? A general question that depends on the use case. Today's session will go over some details. Hypertraining. It's a power optimization trick designed to optimize the problem above of CPU wait time. It essentially tricks the operating system to double the amount of physical code. For example, 10 physical cores becomes 20 vCPUs, which are hyper-threaded. For all intents and purposes, using 20K instead of 2. Latency, we're going to go over that very quickly. Same goes for throughput. Concurrency, everything that is working in parallel. Opening, I mentioned that earlier without explaining it. It's accepted requests per second. VCPU, questions from the audience. VCPU is not only in the cloud. VCPU can be in your server as well. You take a physical server, go to the operating system, you can type a Linux CMD command, and you will see the amount of vCPUs you have. The only way you'll see the physical cores if you disable hyperthreading in your BIOS, or you have a look at the server spec according to the type of the CPU. On the internet, you'll see the actual physical. Yes, I hope this answers your questions regarding vCPU. Okay. Before going a little bit deeper, was that in a good pace? Did everybody were everybody able to follow? Any questions so far? Okay. Moving on. So far, so good. Thank you, Joey. So what you see here is orchestration via Airflow. Airflow, as we said, is an open source Python solution that does orchestration. In the end of the day, if you need to visualize, Airflow is like, or an orchestration solution, it's like an actual orchestration, like you see in music halls, or YouTube performance, concerts, and so on and so forth. So there's one person, the conductor, who is in charge of orchestrating the entire show. If we translate that into data, essentially someone who needs to orchestrate the task being operated in which order and what everybody are doing on which server. In theory, that should achieve, like in music, the harmony you need to run your data pipelines efficiently and in a cost-effective manner. I'm going to mute the newcomers, but you can unmute yourself if you like and ask questions on the chat. Any questions about orchestration before I proceed? Okay. From this moment on, I'm going to slow down so everybody will be able to catch up. So an Airflow cluster, Airflow has the ability to work in a distributed workload, meaning it has an architecture that by design allows you to split all the different services across many servers. There's an orchestration part that is called scheduler, and there's a broker that manages the queue of tasks in order, and there's a worker machines which are actually do the work, and you can scale out by adding more nodes to the system. Question about Airflow cluster orchestration before I proceed to the next jargon? From Chris, Kubernetes orchestrate nodes, containers, Airflow orchestrate tasks, I guess. Yes, Airflow orchestrates tasks. It has about 7 deployment architecture. One of them are Kubernetes worker mode, which makes it both an advantage and disadvantage that depends on your use case. Another question from the audience, can you talk about the dark directory path to machine subprocess versus scheduler broker? Yes, I can talk about it, but essentially in Airflow, you need to assume that there's one folder for the DAGs, for the ETL jobs, and they will be deployed as needed by the scheduler to the different machine. If you are working in cluster mode, you should assume in your code that the machine will run on the DAG will run on several machines. Therefore, you should not assume local storage. You should assume only external storage such as S3, Google Cloud Storage, and so on and so forth. Another question from the audience. What if we have a different task with different Anjuji?
Actually, I could not able to write that question. So my question is like there is requirement like we have different task and every task has a different resource requirement like CPU and RAM. So if we are scheduling a job that contain a different resources, so how we can configure different container with different resources?
Well, if you have a job that is CPU/RAM bounded, then you are using the wrong tool. Airflow should not do anything except orchestration. Thus, any CPU bound or RAM bound workload should be done externally on different machines, not related to the Airflow itself.
Yeah,
Airflow,
that is correct. Like either we can use Kubernetes or we can use ECS Fargate as well for performing these tasks. But the problem is like, for example, if we are using Fargate, so in that case, we have to configure all the tasks and we need to provide all the resources. So if different tasks needed different resources, so I need to create a different images and container.
you mentioned Fargate, if I'm not mistaken.
I mentioned Fargate.
Then I would strongly recommend to consider managing your own ECS cluster for such scenarios. The reason for that is Fargate. Chris.
Yeah, it's Fargate.
It's AWS Fargate.
Yeah, Fargate.
It
Yes,
allows you to essentially deploy containers without managing the actual cluster of Kubernetes of Docker. But when it comes to data, you want to have a control over the size of the servers and the cluster, and you don't want to keep tuning your job. You want to have a big enough cluster to have, according to the high optimized, high bounded CPU RAM task, and then maybe have a cluster for the low bound CPU clusters. Does this help you?
Yeah. Thank you.
Can you help me with your name pronunciation?
My name is Anuj.
Anuj. Okay, Anuj.
Thank you.
Okay, thank you, Anuj. So, continuing. Guys on the chat, thank you for helping. This is keep doing that. It's really helpful that you explain things as we go. So the next slide, this is super critical to understand this slide, so I'm going to slow down. Someone asked about the difference between virtual CPU, vCPU, and a physical CPU. How we know that? The thing is, you need to assume most servers you will work with, either it's a physical server with an operating system with hyper-threading enabled in the BIOS, or it's a cloud, or it's a virtual machine, either of which will be vCPUs. And this is super critical to understand. Why is that? The hyper-threading in the BIOS allows you, by a hardware optimization, to trick the operating CPU and optimize the CPU wait time to trick the operating system to having double the amount of cores. But for intent of software development, more specifically in data, not high performance computing solutions, this is totally different. Only for intent of data processing, consider vCPU as one thread. Okay? Is this clear? As a side note, that one should ask, then if the hyperthreading is so good, why do people use physical CPUs and disable hyperthreading? The question is very simple. The answer is very simple. In specific use cases where latency of CPU wait time is important, then you need physical CPUs. You need to disable hyper threading. The cost-benefit ratio is simple. You'll have more response time. We're talking about some millisecond response time, but the cost of each CPU thread will double. Any questions about this slide before I continue? Okay. So multi-threading. For all intent and purposes, in 80-90% of the use cases, you can forget about physical CPUs and just assume you have vCPUs and each core is coupled with one thread. So if you're writing a Python application called Python application 1, our original, and you are opening 4 threads, then you are immediately using 50% of the CPU for your application, assuming it's constantly working. It's not that trivial because some threads work less and more, but assume 100% capacity per thread. The question one should ask about this is, wait, why am I using only 4 threads? And the answer would be that depends on the use case. If you only need 4 threads because you're only doing 4 tasks in parallel, then this is what you need. In data, naturally, you want to have more and more threads, so you'll have more parallelism. Just imagine, for example, assuming Airflow in this case. An Airflow orchestrator, scheduler decides to shoot 100. Let's talk about numbers like here. 4 DAGs in parallel. DAG has its own task. One could be a few tasks such as 1, 2, and one could be 100. But in the end of the day, Airflow counts the amount of active tasks per second. So if your workload is consuming 100 tasks per second, then you need 100 vCPUs in your workers. As simple as that. Otherwise, you'll end up, no, not 100. You need a number of CPU which is correlated to that number. There's a ratio. For example, 1 to 5. If you're using 100 tasks per second and a ratio of 1 to 5, then you need 20 CPUs, vCPUs. Any questions about this slide? Okay. latency versus throughput. As I mentioned in the introduction, these are two important things. Latency, assuming the x-axis is time, from the moment you request the thread to start, some time passes. This is your latency. And the actual time that the starts is your throughput. So the thread will continue and continue until it ends, and then this is the end of the thread. This is a very simplistic view, naturally. But you can understand now that sometimes latency of 10 milliseconds might be crucial for some tasks, but for some tasks, it's irrelevant. Questions about this slide before I continue? Okay.
మళ్ళీ మార్చారా హెచ్పి అకౌంట్ పాస్వర్డ్
Can you repeat your
అన్నా అనుకుంటారా
Okay, so Cassie, I muted you. If you like to repeat your questions on the chat, please do so. Round robin example. As mentioned in the introduction, round robin is an algorithm that allows you to split the CPU time between two threads racing on the same CPU core. So you have job 1 and job 2, and 1 second mark, and it simply splits the time, say 50% here, 50% here, 1 second here, 1 second there, and then switch between them again and again in a cyclic manner. Yes, Mark?
So I would just regarding your previous slide about the latency.
Yes.
Just allow me to understand, if I understand it right and my way, that I have a latency. This is a fact. When I'm receiving huge amounts of data in WebSocket, sometimes I have latency, right?
Yes.
And from my point of view is, okay, I cannot avoid the latency, but I can decide what I do if I have a latency. How do I proceed? Or how do I proceed during a certain millisecond that is crucial or not? And what do I do with the data if I don't receive it? So am I correct somehow?
You are correct, but let me try to answer that in a different way. You cannot.
Thank you.
You cannot solve completely latency. You can only minimize the time you wait and choose whether you handle this or not. In most nowadays applications, latency of a few milliseconds is meaningless. But in the use case you mentioned, WebSocketing, I don't know, maybe latency is important. So there are two options. You can talk about your use case if you like, whether now or later, or you can contact me in private, and if I can help, I will be honored to help. Notice I'm an expert on data, so
I think that can be reduced with the
okay, thank you. It's not for an open discussion right now.
Yeah.
okay. Then please contact me later, Mark. I'll do my best.
Okay, but what is important from my point of view as an architect, that I have to take in, I cannot avoid latency. I have like, I don't know, 80% or 20% latency or whatever number I have. And since I relay on the data that I'm processing, and it has to be processed in a certain amount of time. And because of the latency, I cannot do that. Then I have to trigger a different, let's say, risk management scenario. Okay, that was the question 4.
So you cannot avoid latency, but you can decide how to minimize it and how to address it. And it sounds like you're doing it. We can do a follow-up at the end of the session or anytime, just contact me via email and I'll be happy to accommodate any question you have.
My pleasure. Thank you.
There was a question from the audience regarding time slicing on CPU. It's the same thing, basically. There are different algorithms to optimize time on CPU. I'm not an expert there. It was just a simple example to show you that one CPU core is addressing two different threads and what happens in the middle. The actual algorithm is meaningless for our discussion. Let's talk on Airflow and how does that work. We talked about the Python application and vCPUs, and we discussed that if you have 100 tasks, that equals, give or take, 20 vCPUs. That really changes from an architecture to architecture, and to better fine tune it, you need to talk to me. But as a rule of thumb, assume 145 for our discussion. And you now know that based on what I said, any task is correlated with this CPU thread. And the trick is to manage your peaks. So if you have a consistent workflow of 100 tasks per second, you always need 20 CPU available. Otherwise, you risk in destabilizing your Airflow cluster and constant crashes in your Airflow. However, if you move your Airflow workloads and you see that it peak for 5 minutes in 1 hour, the rest of the hour it's idle, you can reduce the amount of CPU cores because there's a queue mechanism that allows you to manage a queue before the tasks are being processed, and then you can handle the workload you want to do in which rate. You can manage that and do your own analysis of cost-benefit relation, meaning the 20 CPU servers may be expensive for some deployments and some use cases, but for some it won't be. So if you can do everything in parallel, do it and keep it that way. It will result in a more stable environment and a faster processing time and lower latencies. Any questions about this slide before I continue? Thank you. API use cases. As I said in the beginning of the lecture, this session was born from a real-life scenario question from a customer when he wanted to extract data from third-party APIs with real-time data requests because it's time series data. The dimensions were simple. That was an energy use case, and we needed date, the account ID of end customers, the amount of sites where they generate energy, and the devices per those sites. That means you have a Cartesian product in terms of volume, data volume, and data velocity. Oops, sorry. Which is quite tricky. If you talk about 3 years worth of history, 100 accounts and 100 sites and 100 devices per device, you will have lots of data. That's 1,000,000 requests per single time frame. So if you have a 24-hour use case and you only bring data 4 times an hour, that's about 36 billion requests per year. which is for some use cases and some companies, that's a lot of money. Mark, are you still holding your hand up, or have I answered your question? So when I started talking to the client, the agreement in real time, 15 minutes is in real time. So a frequency update of 15 minutes was more than enough. So the idea was to balance between the use case and the technology costs. So let's do an open discussion. What would you have done for such a scenario? What would you choose and why? Please, don't be shy. Open your mics and start talking.
Stop talking.
Yes, Masudi. No? Anyone? Joey?
I would just say, like, I start with whatever is the most simple solution that solves the use case. If you have to use whatever is the most complex, then that's what you have to use. It all depends what the trade-offs are.
So what would be the trade-off in your opinion for 36 billion events? Mind you, that's 3 billion events monthly. What are the challenges?
Speed. I mean, I imagine speed matters, right? So you have to go a certain amount of speed and velocity. There's only a certain amount of hours in a day, so that's our constraint.
So
and you have to get it. You have to probably, or just to talk. I'm just talking this through. Like, you'd probably have to, know what your baseline throughput is. Like, what's possible within a given time frame.
Okay, let's write it down. So basically, speed, baseline throughput, consideration set. What else would you consider?
Maintenance.
Maintenance, yes. What are the challenges in maintenance? What?
I think to keep the same load that you are that you want to work with the same KPI. Let's say you want amount of transaction in second, and you want to keep working on that rate and not losing it, even if in case you want to manage the data, if you want to like reboot some servers, if you want to transfer the data to other servers, you want to like
Okay. All valid points, all are valid points. Everything you do usually in maintenance apply here. It's a complex use case, lots of servers, lots of maintenance. You want to do some in which nobody mentioned. Anyone else wants to share before I shoot some stuff?
I think the quality of the data.
Sorry?
I think the quality of the data.
Can you rephrase that or explain?
The data quality is basically like, for example, when we are dealing with any ETL pipeline, so we have to validate all, the data source, whatever the data we are getting. So because of that, there are a lot of operation that we need to perform over the data. Because of that, we face a problem on the performance.
Yes. What about the destination?
Yeah, the destination also matter. Whether you are writing it to any database, S3 or any other FTP server. So all have their own.
Okay. Would you consider a different cloud than the one the company is using simply to solve this problem?
So for me, like I'm working on AWS, so I think that is a fast enough. But still, if you're loading a heavy file with the big data processing, it take a lot of time to upload on S3.
Yeah. So allow me to touch about all of these points. Yes, speed is matter, but you need to talk about parallelism. The subject of today is parallelism and how you utilize most of your architecture in this advanced ETL. Someone asked in the audience about ELT and ETL. A bit not relevant for the discussion. We can do it later on in the Q&A phase if you like. But the key point is parallelism, because you need to address 100 accounts and 100 IDs and over 100 devices all in a matter of seconds, because you need to approach these million requests in parallel. You have a window of 15 minutes to accomplish that, but still, you need to issue a million requests in that second. That's the challenge. So a baseline throughput, you need to naturally understand how much time to get the entire, let's call it interval, specific interval, 1 million requests every 15 minutes. Because if it's take 1 second or 10 minutes, it will change the way you think. Maintenance, naturally, no need to go deeper there. Data, what type of operations definitely matter here. So you need to consider here whether using code or that. Do you need something hardcore like Hadoop? Yes, no, so on and so forth. Like Spark.
And I think that the programming language also matter.
Yes, programming language, that's here, programming lang. Okay, destination and DB definitely matters, and which cloud? I would say that in some organization it's relevant, because sometimes you can switch cloud, cannot switch cloud easily, but sometimes you can, and sometimes there's a better cloud for this use case, but not always. Any questions before I proceed about the use case? Okay, concurrency versus parallelism. In this use case,
I just would like to add my point of view to this use case because it relates to my question before. Since we're dealing with APIs, then I have a response time. I'm making a request on the web to somewhere, and I have a response time. And this response time is crucial because I have to make, I can make one API request a second or more, or depends on the size of the data that I'm requesting. So I think I would add to this slide that to filter the unnecessary data during the process.
Yes.
So eventually you will be dealing with less data.
That's called in-flight analytics.
Yes.
In most cases, I would recommend, I wouldn't say most, in some cases, I would recommend in-flight analytics, but in some cases where the volume and velocity is not exponentially growing, I would recommend to keep everything and filter out later.
Yeah, this is one concept, but I'm doing this on like daily basis, and I'm getting data that it's not necessary for me, so I don't process it. So I don't put it in the cycle in the database eventually because I don't need it. If I will need it, I will process it. But right now I don't need it, and in order to process some extended data, it takes more time, and this time is crucial. And
Yeah.
it's about hundreds of milliseconds. This is my opinion. So,
yes, I understand what you're saying, but please consider the following architecture and leave it at that. If you like.
yes,
Just fork to another ingestion layer that takes all the bad data and continue only the good data via data pipeline. The reason for that is that you want to analyze the bad data and to understand what's wrong and maybe talk to your source data provider. Because it's costing both sides money. Maybe there's a bug. Maybe you want to see that because it's an abuse of your system. So I would consider that. Okay, solution alternatives. We are going to talk about 3 alternatives today. I talked with the client and I'm going to share with you my view on that. So one would be the obvious, use a Python script, use multi-threaded, and you can achieve the target that way. The second would be use AWS Lambda, which is a serverless service in AWS that allows you to run specific code snippets and essentially launch a Docker, run it with CPU RAM, run your script, and then when you're done. This is a rather common use case, and lots of AWS solution architects refer to that. We're going to talk about that as well. There's Airflow scripts that naturally. Don't know why I did it 1, 2, 3, but maybe number I didn't. Python, Lambda, Airflow. Okay. Okay. So the pros and cons of Python script. Well, it's not trivial for most of us, I assume, because if you're here, you're naturally highly technical.
I think in case of Python and multi-threaded, seems to be we have a disadvantage in Python because of something called GIL.
GIL.
And this GIL is like a global interpreter lock, and you cannot like it protects the access to Python objects, and this is the reason Python won't be able to execute multiple threads of bytecode at once.
I wouldn't go that far, but I would say the following. You can replace Python for this discussion in any programming language you prefer. The reason why I choose Python because it's consistent with Airflow as a paradigm. It's also Python, and most of data engineering advanced packages are in Python. So in the end of the day, don't need to manage 2 types of languages, but I agree there are better languages to do multi-threaded scripts, especially when you need low latency. Thank you for your comment. But the reason I did talk about Python, it's easy to get started, easy to implement. It's usually not a new technology. When we talk about data engineering, you need high degree of programming skills to make it work. I'm gonna admit you. You need to do a lot of code to perform error handling in your ETL job. Performing retry and replay operations is non-trivial, and concurrency is only limited to your server capability. Running the code that runs in a distributed cluster is complicated. And in the end of the day, you are limited to the RAM of the server capabilities. And on top of that, if you solve all of the above because you're a super duper developer, you won't be able to handle easily the throttling of the source API. That means that you will write a code so good and so fast that you will be requesting so much that the vendor will simply deny a request, and you need to handle that. And that will become very dangerous in your code and very non-trivial to handle. If we talk about AWS Lambda, it's easy to get started, easy to implement, very scalable. You can issue 1 million threads in parallel easily. It's trivial because you only do the point of code that handles the logic of your code, and it's serverless, so there's much less maintenance. The cons. It's usually on-demand costs. That means if you compare that to an EC2 machine, an EC2 machine will be cheaper, assuming 24/7 utilization. The service itself is not optimized for data operations, meaning replay operations. You need to manage and write code for that, and functions or optimizations you can do. So it's not ideal for data pipelines. Talking about Airflow as a third alternative, it essentially by design makes the concurrency issue and scalability issue very trivial. All the replay, error handling, retry, and throttling issues are trivial. It's more cost effective than AWS Lambda because you can use spot instances, and you can do reserved instances, and you can do long-term discounts. The challenge is about performance tuning. It's very painful if you don't know what you're doing, but the good news is if you get a console for that, within a few hours you can optimize your cluster forever. And the only downside that remains is that it requires much more coding expertise to make it simple and efficient with low maintenance. Any questions about the alternatives before I proceed? Okay. So if we do a competitive analysis in terms of performance, Python out of the three will be naturally the best because both Airflow will have an overhead and Lambda, but in Lambda it will be more minor. In terms of scalability, managing your own scripts is the worst, but AWS Lambda is the best, meaning if you have 100 times more use case, then 100 times more events per second than what we discussed, and AWS Lambda will be far simpler by an order of magnitude. And Airflow is limited to an amount of connections per second. I mean, even if you take a really distributed cluster, very strong, lots of CPU cores, I never tested that for anything larger than 10K. In that scale, it's about as good as it gets, let's put it this way. In terms of cost, naturally, it will be easier with cheaper, more cost-effective with Airflow. In Python, it will be relatively low. And AWS Lambda would be the higher costs, not highest, higher. In terms of maintenance, managing your own script would be high maintenance. Airflow would be medium, and AWS would be simple. So a question from the audience, from Anush, how do we do scalability in Airflow? You can configure in the configuration of Airflow how many processes of tasks in parallel, and you just need to ensure enough CPU cores to support your scale. The question about the parallelism from Chris. Can you explain AWS Lambda? AWS Lambda, and the reason I mentioned that because it's a serverless service in AWS to take one piece of code and runs that in parallel 1 million requests. Meaning, imagine a scenario for each request out of the million requests over here. You issue one container, one AWS Lambda function that runs your piece of code, and you only change the ID of your account device. It will run 1 million instances of that same request, just different IDs, in parallel. Essentially, this is your concurrency and parallelism. It's the same thing in this use case. Does this answer the question, Chris? Okay. Thank you very much. Multiple functions together in parallel, yes. So if someone keeps bugging me, I don't know why, over the phone. So let's talk about the summary. So we learned about this use case. The idea is that in the end of the day, the work of the architect is to balance between the business use case and the technology, and to make sure that the use case is all about cost effectiveness. And this framework is something I created over the years. We started teaching about data and architecture and talking to the community, and I realized it's not that trivial to understand. But at the end of the day, the job of the architect is to balance between these three focals. It's a matter of response time, which is performance, cost effectiveness, and simplicity of maintenance. So a good architecture will implement 2 out of 3. A bad architecture will only implement 1 out of 3, but it's not always achievable to achieve 3 out of 3 focal point. So this is why I drew this as a triangle. If there's something I want you to keep in mind, is this session. Okay, I want to thank you all for today, today's session, and the recording will be uploaded to the website.
Thank you.
Feel free to send me questions, guys.
Thank you.
Thank you.
Thank you. Bye-bye.
Thank you, Omid. Bye-bye.